A Carnegie Institution for Science audio press release for October 20th, 2014. Wild molecular interactions in a new hydrogen mixture. Hydrogen, the most abundant element in the cosmos, responds to extremes of pressure and temperature differently. Under ambient conditions, hydrogen is a gaseous two-atom molecule. As confinement pressure increases, the molecules adopt different states of matter, like when water ice melts to liquid and then heats to steam. Thus far, at extreme pressures, hydrogen has 4 known solid phases. Now scientists, including Carnegie's Alexander Goncharov, have combined hydrogen with its heavier sibling deuterium, which has an added neutron in its nucleus. They created a novel disordered phase 4 material where the molecules interact differently than had been observed before. The new results, published in the October 21st issue of Physical Review Letters, could be valuable for controlling superconducting and thermoelectric properties of novel hydrogen-bearing materials. Phase 4 of dense solid pure hydrogen and deuterium was previously discovered by several members of the same team and others. The hydrogen molecules exhibited 2 very different behaviors. One weakly interacted with its neighboring molecules, while the other strongly bonded with its neighbors, forming hexagonal atomic sheets like graphene. This was a novel, truly two-dimensional form of carbon with fascinating electronic properties. Electronically, these layers behave somewhat like a semiconductor and a semimetal. Semimetals are in-between metals and semiconductors with respect to their electronic properties. This team, led by Ross Howey of the University of Edinburgh, combined experiments and theoretical calculations. They mixed the pure hydrogen and deuterium in varying concentrations and subjected them to room temperature under different pressures, ranging from about 2,000 times atmospheric pressure, or 0.2 gigapascals, to about 2.7 million atmospheres, or 270 gigapascals. Goncharov explained that before conducting the experiments, the researchers thought that the material could change under pressure by several different processes. The mass differences of the molecules mean that they have very different low-energy states, which would affect the outcome. In one scenario, the physics could result in the ordered segregation of the hydrogen and deuterium molecules between strongly and weakly bounded layers. Under another scenario, the molecules might be randomly or disorderly distributed. Then there's another intriguing prospect they entertained. Whether the disordered state affects the waves of atomic vibrations, called phonons, and prevents them from freely propagating, a phenomenon called Anderson localization. Typically, electrons in solids have energy values only within certain ranges. The scientists thought that vibrational wave propagation through a molecular maze might break this energy band depending on the strength of the molecular bonds, the masses, or both, and could affect just a few local molecules. The scientists use a technique called Raman spectroscopy, which measures the tiny quantum behavior of vibrational energy, rotational energy, and other motion in a molecular system when a laser light interacts with the molecules. They then confirm their experiments with theoretical calculations. The scientists found that above 1.9 million atmospheres, the vibrational waves show Anderson localization. The extent of this localization depends on the concentration of hydrogen and deuterium and whether these molecules belong to weakly or strongly bound layers. For instance, in one layer, hydrogen molecules vibrated in separate groups of 2 to 3 molecules at frequencies that weakly depended on the neighboring environment. As the hydrogen concentration increased, the different hydrogen clusters grew and started to couple. This is the first study where Anderson localization from vibrational energy has been observed by interacting with mass differences in a material. Goncharov remarked that the Anderson localization of vibrational excitations in hydrogen mixtures provides a new mechanism for optimizing thermoelectric and electronic behaviors, for example, in superconductivity. With the independence for nimble pursuit, Carnegie scientists tackle some of the most profound challenges in modern science, fundamentally changing what's possible for us, our planet, and our universe.